Okay, so for everyone who's here, I'm just going to give everyone a minute or two to hop on the chat. And then I'll get started in a couple of minutes. Okay, while we're waiting for people to join, if you have, can you just pop your year group in the chat so I know sort of a bit more about how much you've covered and stuff like that. Okay, we've got year 11, excellent. And I just wanted to ask, was there another lecture or anything that you were at before? So trying to gauge how long I have to wait, because if we're not waiting for everyone, I would like to get started. I'll give them until 5 past to come in. So for everyone who's joined now, if you just pop your year group in the chat, that would be great. Just so I know what your background knowledge is. Okay, you've got year 11, year 10. Okay, and another year 10, excellent. So I'm just waiting till 5 past. If the new joiners could just pop your year group in the chat, just so I know what your background knowledge is. So this lesson is going to be about, so all of these lecture theories are about electricity. This one specifically is going to be about current, potential difference, some basic definitions, and an introduction to how circuits work. And by the way, I just wanted to say, if you have any questions, could you put them in the chat and not the Q&A, because my Q&A is not working. Okay, I've given them 5 minutes now. So let's jump into the lesson now. Again, I'd just like to say, if anyone's got any questions, please just pop them in that chat. So GCSE Physics. A quick bit of introduction first. So hi everyone, my name is Darina and I studied chemistry with molecular physics at Imperial College London University. And today we are going to be covering current and potential difference. So a little bit about how circuits work. We'll be covering all the circuit equations that you need to know at GCSE. We're doing a special extra bit on resistance and then looking at some special components. So let's move on to a general sort of overview of electricity at GCSE. So there's a few things that come into electrical circuits. So our next lesson, for example, we'll be looking at dangers and safety. We'll be looking at uses inside and outside the home. And in a couple of lessons, we'll be looking at energy and power and how different components use energy and power. But today, we're going to be looking specifically at current, voltage, and resistance. So that's everything on the top right of this diagram. And The first part of that is, well, how do circuits work? So we have got, when we wire up a circuit, essentially what we have is we connect different conductors together, usually they're wires, and this means that electrons can flow around a circuit completely. So that's what a complete circuit is. And a battery essentially just pushes those electrons around the circuit. And what you have to remember also is that we say that current goes from the positive side of the battery to the negative. So that's what I've tried to draw on these diagrams. We've got current traveling from the positive side all around to the negative, and on a circuit diagram, that is shown as the longer end is positive and the shorter end is negative. Now you can remember this any way you want, but usually I remember it as the shorter side, that looks like a little negative sign. So negative, small little negative sign, that's the negative side. The other side is going to be positive. Electrons flow from the positive to the negative. Okay, great. So just to understand circuits a little bit, so basically what we have is we have the electrons in the circuit, which are the ones actually carrying the charge, and then we have the ions, which are basically the rest of the components, right? So it's the stuff that the other stuff, the metal ions, that the wire is made of. And essentially, when a voltage is applied, it causes the electrons in this wire conductor to move towards the battery. So we have negative, positive, the electrons are moving around like so. And that's actually what current is. It is the movement of electrons. Why can't, okay, well, can't we make a circuit out of something like string then? Would a string circuit work? Can anyone tell me? Yes, no, any thoughts? Just pop it in the chat. No, and why wouldn't it work? Why wouldn't a string circuit work? Can anyone have a go? Okay, so we've got some ideas there. Basically, the string circuit, well, we know intuitively that it wouldn't work, but the main idea is because the string doesn't have, it's not a conductor, it's an insulator. It doesn't have any free moving electrons to carry that charge. They can't move throughout. They're not free moving, so we can't have a current and we don't have electricity. So that's really important to understand how current behaves in a circuit. Okay, so here I've got a bit of a fill in the gaps exercise for people who sort of know something about electrical circuits but just need a refresher, or if you just want to have a go, that's all right as well. So these are the words that you're choosing from, and I just want you to have a go. Let's start with the first one. So that little blue section, we've got electric current is when electrons start to flow around a circuit. So we use something, and it is measured in something. So this is about current. Any ideas what these gaps could be filled for? So we've got some ideas. Just put the two gaps. What can it be filled for? Okay, we've got some ideas already. If people could keep going, that would be great. All right, we've got some ideas. If you're wrong, don't be shy, that's okay. All right, so mostly we've got two ideas coming forward here. We've got a voltmeter or an ammeter for the first start, and volts or amps for the second. Now, it's really important to remember that this is current we're measuring, electric current. Electric current is measured in amps, and it's measured using an ammeter. So the units of current are amps. Okay, let's go to the second sentence. So let's put those in. So we've got, oops, too far. Oh, so potential difference, also called blank, is basically how big the push on the electrons is. And we use a blank to measure it, and it's measured in blank, a unit named after volt. Can anyone have a go at this? Just put it in the chat. If you want to have a go. Right, so we've got some answers. And again, well, this is voltage, right? And just like the name is giving the idea, we use a voltmeter. So it's called voltage. We use a voltmeter to measure it, and it is measured in volts. Great, well done, guys. So, okay, resistance, that's the last thing that we have to think about today, is anything that resists an electric current. And, based on what's left from the words, what do you think it's measured in? So again, if you just have a go, even if you're not sure. Right, great. So by process of elimination, that's probably just going to be ohms, right? And indeed, resistance is measured in ohms. So let's have a look at these terms in a bit more detail. We get our circuit equations. And circuit equations are useful for calculations in circuits, but they're also useful for us to define the actual terms we're talking about. So again, let's start off with a concept called charge. Does anyone know what charge is measured in? Or what charge is? All right, okay, we've got some answers. We've got what charge, so we've got coulombs. Excellent, well done. And what is charge? Can anyone give me a wordy description of what charge is? Right, well, the flow of current and the flow of electrons, that's all pretty much grouped under current usually. But the most important thing about charge is that it's basically a big lump of electrons. So as I said, charge is measured in coulombs, but a coulomb is literally just a group of electrons. And the way to imagine this is that, well, theoretically, we could count each time an electron goes past, but that would be pretty hard, especially because electrons are tiny and there's loads and loads and loads of them. So instead, what we use is 1 coulomb is a group of lots of electrons. And that's what we subdivide charge by. We say that an electron actually has a fractional charge. So it has this tiny charge of 1.6 times 10 to the 19. So that's what charge is. Just imagine it as a big blob of electrons which have a particular charge. Remember, charge is a property that electrons have, so they have negative charge, whereas protons, for example, have positive charge. So this is just a unit that humans have used for their own convenience to measure charge. Right, let's go over to the next one. So charge yet doesn't really have too much of an equation, but we're going to use charge on our next one, which is current. So we've just talked a little bit about what current is. I've tried to draw it out for you. So anyone have any idea what current is formally defined as? And if you can remember, what is it measured in? And we've just mentioned what's it measured in. That first, can anyone tell me what the units of current are? Amps, excellent. And the abbreviation is A. Yes, well done, everyone. And what is a definition of current? So we usually tie this to an equation. So if you can think of an equation to find current, that would be really good. Right, the flow of charge, the flow of negatively charged electrons. But what's really important to notice here is that it's the rate of flow of charge or the rate of flow of negatively charged electrons. So the equation that we use to describe it would be this one. So it would be I equals Q over T. Now it's really important to include that T because that is the rate of flow of charge. And obviously, as you said, the units are in amperes. That's our first equation that we have to remember from electricity. It's I equals Q over T. Okay, our next equation on our next definition is potential difference. I mean, we've already mentioned as well. Now, potential difference, this equation is a little bit hard to get. So I've already put it up there for you. So V equals W over Q. Can anyone put that into words? What does that actually mean? What does that mean that potential difference is? So I've already described potential difference as sort of our pushing power, right? But that equation, yes, so someone's brought up the resistance equation. We'll get to that in a second, don't worry. We will get to that. But first, in terms of volts, okay, let's start easy. Again, what are the units of volts? Anyone got the units of potential difference for me? What is the units of volts? Okay, we've got V, yeah, so that's going to be in volts, excellent. And using that equation, we can actually also define voltage to be essentially the energy lost between 2 points in a circuit per unit charge. So if you have a light bulb where you need to use a lot more energy, so okay, W is work done here. You also sometimes see it as an E. So it's either an E or W. Because work done and energy transferred is the same thing. I hope that answers your question. So W equals work done, but this equation can also be written as E over Q. So that is exactly the same thing. Okay, so this is our then definition of potential difference. So basically the work done per unit charge or the energy transferred per unit charge. The way that I imagine it in my head is, again, if I have a bigger voltage across a particular light bulb, then I am spending more energy. So each electron, each coulomb of charge is transferring more more energy to that light bulb. or it's, the work done. So it can be defined in both ways. Okay, great. Now, the last part is resistance. Now, I know some people have been mentioning this chat already, but how do we link resistance into this whole picture? What's our equation for resistance? Right, great. So we've got, so we're linking voltage, current, and resistance. We've got some ones to do with power, but what I want to do is link together voltage, current, and resistance. Can everyone have a go? What's the equation for that? So we've got a lot of Ohm's law. Yeah, that's correct. We'll get to that. Okay, V equals IR is the correct equation. And we can rearrange that to be resistance equals voltage divided by current. So that's the equation with which we actually define resistance. So I said that it was measured in ohms. We went through this before. And basically, it is the ratio of potential difference across a component to the current flowing through it. That's not a very nice definition for us to remember. So here, if you've ever asked for it on an exam, you're going to be saying, okay, resistance equals voltage divided by current. That's its definition. That's how we find it. But if you want to imagine resistance in your head, I would say that you would need to have basically, how hard is it for electrons to move through this thing? If the resistance of a component is higher, that means electrons are both going to be slowed down by it more. So that means that your I on here, so let's have a look at this. We have, if the resistance increases, the electrons are going to be slowed down. So the current will decrease. So there, it's going to go down because they're inversely proportional. And we also have, and there are some questions about resistance, which don't worry, I will answer later on in the session. We're just not going on to that yet. And then we have voltage, which, okay, so basically, if the resistance of a component is high, it's harder for electrons to move through. That means they're going to spend more energy moving through that resistor. So your voltage will be higher. You're spending more energy per coulomb. So define it in your head as how hard is it to move through a component. If you're ever asked for it in terms of an exam paper, you would say voltage divided by current, because that's the correct answer. Right, so let's go a bit, so we've got a couple of answers already, questions already about resistance. So let's go a bit more depth on resistance, because it's kind of the most unusual concept here. So let's try and understand resistance. So again, we've got our electrons and our ions in our wire, which are the conductors which make up the circuit, right? And if a resistance was to get higher, a couple of things could be happening. For example, the ions could be vibrating and getting in the way of the electrons. So that means that the electrons will move more slowly through the material. And this is resistance. Again, this effect also causes metals to heat up. Or alternatively, you could be shining lights on electrons or whatever and giving them energy. So that makes the electrons move faster. So we've got two effects going on. One of them is more collisions. Therefore, electrons are slowed down. And another one is, okay, so everything has more kinetic energy, so there could be more collisions, but there's also more energy given to the electrons. And these two factors work hand in hand. And we're going to have a look a little bit later on about how we can explain different components resistances with them. Right, but going back to our basics, so this is the resistance equation written out as a triangle. So this is just ohm, who the unit is named after. And we have something called Ohm's Law. And this is what you were all mentioning when you talked about your equation. So resistance equals voltage divided by current. You also have a triangle that you can form out of this. So V on the top and IR on the bottom. So remember how to use triangles. You just cover up what you want and you're left with the other two, current times voltage. Now, someone was asking about what to do when you have what to do when you have resistance in series and resistance in parallel. I will get to that actually next lesson where we compare series and parallel circuits. So you'll have to come back next week for that. But I might give you a quick answer at the end of the lesson. Right, so a few more basic ideas as well about how circuits work in general. So now that we've got all the terms defined, let's go a bit more in depth and hopefully we can understand a bit more about how they work. So I've got a couple of circuits here and I want you to have a think about these statements. So firstly, we've got two diagrams here and I say that if a battery is added, the current what will happen to it? Increase, decrease, stay the same because there is a greater what on the electrons. Okay, so we've got a couple of answers already. Have a go. If you're not sure, have a go anyway. So we've got some people giving conflicting answers. Remember the first, so the current will either decrease, increase, or stay the same. And okay, so we've got some people changing their opinions. All right, please do have a go. Right, so the correct answer, as most of you got, well done, is increase. The current is increased because remember I said that the battery is kind of the pushing force of the electrons. If we add another battery in, there is a greater force on the electrons, so they will flow more quickly. So we have a higher current. So the current will increase. If you didn't understand that, please just drop a clarification. Otherwise, let's have a go at another question. So this time, we have got 2 bulbs in a circuit. And I want to say, okay, if a bulb is added to the same circuit, what will happen to the current? So if you add a bulb, what will happen to the current? Okay, and why? Why will, well, whatever you're thinking, why will it happen? What's that second gap? Okay, so we've got a couple of answers. Okay, right. Okay, well done. So we've got a couple of correct answers coming in. Well done. So there is more resistance in the circuit. Remember, every single component has resistance. The electrons are going to be traveling more slowly through light bulbs than they are through really good conductors, such as wires. So the correct answer there is if a bulb is added, the current will decrease because there is a greater resistance in the circuit. Now, someone mentioned current having to be divided between the bulbs. Remember, current is just the rate of flow of charge. You don't divide up current, you can divide up voltage in this case, in this circuit. You can divide up the amount of energy that each bulb has, but current will be the same because there's just one path and electrons flow at a certain speed around it. Remember, current is the rate of flow of charge, and they're all flowing at the same rate around this circuit. All right, excellent. So just to recap what we were saying then, so back now that we have our definitions of everything, I think we can imagine this a bit better. So we have our battery, we have our electron, which is being pushed by the battery, and it's basically, a really important idea also is that for wires, we always assume that resistance is really, really tiny. So that's why when we add an extra bulb, the resistance jumps up, because bulb compared to just wire is a massive jump in resistance. So we basically assume that there's no resistance in the wires, which is more or less accurate. Okay, then the electron goes to the lamp, and here the electron arrives at the lamp and transfers its energy to the lamp and then goes back to the battery, where again it kind of loads it with energy and keeps going around the circuit. Does anyone have any questions so far? So when the electron arrives at the bulb, energy is transferred to the light bulb, and then comes back to the battery and is loaded up with energy again. Does anyone have any questions about that? If you're typing that out, I will answer it in just a sec, but I'm just going to move on to the second slot. So an interesting effect that comes out of this is called the heating effect. Now, the heating effect is really important to consider, especially when you're doing experiments. So for example, let's, if you were trying to heat something up, then it's really useful. But if you're trying to avoid a temperature change, for example, as a control variable in an experiment, then you completely don't need that temperature change. But let's have a look at somewhere where this is useful. So here I've got an example of an old-fashioned filament light bulb. I'm not sure if anyone even has these in their house anyway. They're not very energy efficient. They mostly just are there because you haven't switched. You've got an old house, you've got old light bulbs. Essentially, the way that they work is you've got this filament in the center, which is what you see inside the glass. And when you run current through that wire, it's a really thin wire. There's loads of resistance in that wire, and it very quickly heats up. There's all these electron collisions, electron ion collisions. They're all producing sort of waste energy, but actually in this case, we want it to heat up because when it reaches a certain temperature, the filament glows, and that's because it's reaching such high temperatures. So filament light bulb, heating up of the filament causes the metal to glow, which is what gives us our light. So that's an example of the use of the heating effect. So yeah, it causes filament to emit light, but it also causes a lot of energy to be wasted into environment. And as I said, a lot of these filament light bulbs are being replaced by more energy efficient ones. All right, so using that equation that we've been using then, Ohm's law, I want you guys to have a go at these calculations. So get out a calculator if you can and have a go starting with question 1. So if everyone could have a go at question 1, that would be great. And then once you've got an answer for question 1, just pop it in the chat. I'll give everyone, a minute or so to grab a calculator and have a go. I don't mind if your answer's wrong, it just means I need to go through it again. So just, okay, I'm getting a few answers already. Everyone have a go. Okay, great. We've got a couple of answers coming in. Well done, everyone. So the answer is correctly, as most of you have it, is 3 ohms. Well done. Okay, let's try question 2. All right, again, we've got a couple of already correct answers. So that's 4 ohms. What about question 3? Yep. Okay, got some correct answers. Well done. 6 ohms. And then finally for question 4. We've got 20 ohms for the last one. Well done. So that's 20 ohms. So just know how to use this equation and you'll be completely fine. I'm also just bringing your attention to that ohm symbol again. Know how to draw that. That's the symbol for ohms, that little omega symbol. Right, great. The next thing that I wanted to mention is what Ohm's law actually means. So when we have Ohm's law, basically, if we rearrange the equation, we can map it to a graph. So we have, usually we have V equals IR, but in this case, usually, unfortunately, graphs are drawn out with current on the y-axis and voltage on the x-axis. So if we wanted to rearrange it in the form y equals mx plus c, we would have to do I equals 1 over R times V. So that means that's our y, that's our m. Remember, m is gradient, and that is our x. So since this is true all the time for a ohmic resistor and resistance doesn't change, what are we expecting to see from that graph, that IV graph for an ohmic resistor? Anyone put in the chat what you're expecting to see from that graph? Right, so we want to see a straight line, someone's put in the chat. Great. So a straight line, and would there be a y-intercept? Where would it intersect the y-axis, just from our equation down there? Right, great. It would not have a y-intercept. So we have a straight line going through the origin. And can someone tell me what kind of graph that is? Y equals, yeah, so it's a linear graph, and most importantly is a directly proportional graph. So we have a straight line through the origin. These are both criteria of a graph to be directly proportional. So for Ohm's law, for an ohmic resistor, we can say that V is directly proportional to I, and I is directly proportional to V. That's how we get a straight line through the origin. And R, resistance for an ohmic resistor, is constant. So we don't have a change. Now, this means, so Ohm's law only works under a constant temperature, which produces a constant resistor. So ohmic resistors, think just normal square resistors that you've used in your circuit diagrams. For something like a filament light bulb, which we just covered, do you guys think that the light bulb is an ohmic resistor? Yes or no? Right, we've got a lot of no's, and that is the correct answer. Yes, the light bulb is a non-ohmic resistor because there is a temperature change there. Ohm's law and this graph only works for a constant temperature. So for the filament light bulb, we actually see that the resistance is not staying constant. When there is a higher current, is actually, remember we were talking about the collisions with the electrons and ions? In a filament light bulb, the electrons and the ions collide with each other, meaning that you have a higher resistance. It's harder for electrons to get through, which makes your current drop down, and therefore your filament light bulb does not behave as an ohmic resistor. This effect can also be seen if, for example, you leave your experiment running for too long. So you've got an experiment and you're using something which you think is an ohmic resistor and you're trying to keep the temperature constant. Why do you think it might be a good idea to raise the switch between experiments? Does anyone have any ideas? Why do you think you should raise the switch when you're not using the circuit setup between taking readings? Right? We've got a couple of answers. Anyone else got any ideas? Okay, so basically, so we've got an idea so it can cool back down, for example. Yeah, so it doesn't allow the temperature change to get high enough. In fact, you can always say, so it doesn't allow the current to get high, for the resistance to get high enough for the temperature to change or anything like that. That would be correct. So our temperature is still our controlled variable. Well done. So that's Ohm's law. And we have ohmic resistors and non-ohmic resistors. Non-ohmic resistors, an example would be a filament light bulb, and we'll see some more in a second. Here I have an example question of a circuit setup then, now that we've covered the basics. And I want to introduce to you a few ideas. So for resistors in normal circuits in series, you just add up the resistances. So if the resistance of each of those bulbs was 1 ohm, you'd add them all up. Now, also the circuit diagram is the first time you've seen a voltmeter and an ammeter. So I'd just like to emphasize that a voltmeter is connected in parallel. What this means is that there is a separate little branch across the points that you want to measure it over. And this is really important because remember, we said that voltage was defined as the energy change between 2 points in a circuit per coulomb of charge passing through. So the voltmeter is basically measuring the change in energy from this point to this point. That's what that voltmeter is measuring. And remember, we also said that current was just constant throughout this circuit. And this means that we can put the ammeter anywhere, but it has to be in series. And this means that it's just connected, dot to dot with the other components. That's where an ammeter goes. What the question is asking you here is, what is the resistance across this bulb? Well, you need to actually apply Ohm's law in practice now. So you've been told the voltage across that bulb, you've been told the ammeter, which means that the current is the same all around the circuit. So can anyone tell me, what is the resistance across this bulb? Okay, we've got some answers. Everyone have a go. Okay, well done. Everyone's giving more or less correct answers. So yes, correct. We've got 5 ohms there because we use R equals V over I. So we use 10 volts divided by 2 amps. This means also that we can figure out the total resistance of the circuit, keeping in mind that I just said that when they're connected dot to dot, like back to back to each other, we can just add together the resistances. So what would be the resistance of the whole circuit? Right, great. We've got some correct answers. Can anyone? Ooh, so we've got 5 ohms again. Remember, 5 ohms is just a resistance of 1. You've got 3 bulbs in this circuit, so it's not going to be 5 ohms. Yeah, okay, so the correct answer here would be 15 ohms. You've got 5 plus 5 plus 5. Okay, great. So the next thing that I wanted to talk about was these 2 components. Can anyone name me them? So starting with the one on the top left, what is that? Oh, okay, someone said LED. That's not quite an LED. An LED looks like this. So an LED is a light emitting diode, and diodes have a little arrow sign to show the direction current in which they're basically allowed to go. So a light emitting diode would look like this, and this isn't a light emitting diode, not an LED. These 2 are resistors. Okay, so a general resistor would look like this, right, with a little rectangle. My poorly drawn version of a rectangle, but nonetheless. Right, so that's just a normal resistor. That's usually an ohmic resistor. So we've got a couple of ideas here. We've got a fuse, Not quite a fuse. A fuse would just be with a line straight through it. Oops. With a line straight through it. So that's not correct. Any other ideas for what any of these are? So they're resistors now, we know. And we've already had a chat about why it's not an LED, it's not a fuse. Ooh, don't worry about transistors. Transistors don't come up on your GCSE spec. And we've got an idea of a variable resistor. So again, remember variable resistors, they have an arrow drawn through them. That's the vary. Okay, I can tell that no one can quite remember. That's all right. Let's recap this. So usually when you have a circle and it's got arrows coming in, that means that light is somehow hitting that component. So in this case, we've got a light dependent resistor. This is sometimes abbreviated to an LDR, light dependent resistor. And then on the bottom right, we have a thermistor, and this one is affected by temperature. So basically the two resistors that we have here, one that its resistance is affected by light, and one where its resistance is affected by temperature. Does anyone have kind of like a vague memory of seeing these now, or is it new content? Can anyone remember this? Just want to see where you're at. Okay, so we've got a symbol. Why is the variable resistor the same symbol as a thermistor? It is not. So in a thermistor, we've got a flat section here, which basically signifies it as a thermistor. In a variable resistor, you've got an arrow running through it to signify that you can change that resistance. So it's like a scale, right? You can go up or down. A thermistor has a flat bit instead of an arrow. So they're not quite the same. They're just a little bit similar. Okay, great. And remember, someone said a fuse. A fuse looks like this. So you have, your normal resistor symbol, but then the fuse has a line straight through it, and that symbolizes the little wire that is going to melt in the fuse, and we'll be covering that next lesson. Right, so a little bit about LDRs and thermistors, and remember, light-dependent resistors. Basically, for a light-dependent resistor, you have a graph where when when light intensity increases, resistance decreases. Now, if you've been keeping track of what we've been doing so far, you might think this a little strange. So for the filament light bulb, when you have an increase in energy, you have more collisions, and therefore the electrons are slower. But here you have the other way around. So, in a thermistor, when the temperature increases, your resistance goes down. So what's happening here? Here we have a yes. So someone's just asked, does a thermistor change the resistance dependent on temperatures? Yes, it does. So remember, light dependent resistor, as the amount of light increases, the resistance decreases. Thermistor resistance, as the temperature increases, again, the resistance decreases. The effects are a little bit confusing when we compare it to a filament light bulb, but let's think back. Remember, I said that there were two factors impacting here. For the LDR and the thermistor, basically what's happening is that the more energy is provided to them in the form of either light energy or thermal energy, the more energy the electrons have, so the faster they can travel. The collisions are happening as well, but due to the differences in these materials, one factor is outweighing the other. So can someone explain to me in their own words, I'll give you a couple of seconds to think about it, really, really brief. Why does the light, for the LDR, why does resistance decrease but light intensity increase? So I've explained it in terms of the thermistor. So when you have a thermistor, you supply it with thermal energy. Now it goes into the kinetic energy of the electrons, and therefore the electrons can move faster. Can someone make the same explanation but for a light-dependent resistor? I'll give you a minute to type it out. And please, please do have a go. If you don't get it, that's all right. So have a go, and when you're done, put it in the chat. It just has to be half a sentence, nothing complicated. Yeah, Excellent. So we've got a couple of answers there. So as here, we have more energy provided in the form of light. And again, this is transferred to the electrons so they can move more quickly. So resistance decreases. Right, perfect. So how do we use them in circuits? Well, in circuits, we can put them to control certain components and how they work using either light or temperature. So here's an example of a circuit with a with a thermistor on it, and it's a thermistor connected to a light bulb. So in this case, maybe it could be an indicator of some sort. So when the temperature maybe goes so if you want your light to turn on when your temperature is below a certain level, right? So that means when the temperature decreases, you want your light to go up when the temperature is above a certain level, right? You don't want to go above a certain level. You want to give you an alert when that happens. So what you do is you put a thermistor in there, and if the temperature gets above a certain level, then the thermistor will have a really, really low resistance at that point. So your light bulb will turn on more brightly because the resistance of the circuit is going to be lower. So that's an example with a light bulb. Alternatively, you could equally put an LDR in that circuit, right? So if I replace that thermistor with an LDR, can someone think about a location where they would use a circuit like this? So where would it be important being able to control a lamp with a light-dependent resistor? Any ideas? So anyone got any ideas where? Okay, we've got a couple of ideas. Well done, you guys. So to stop fires, remember that we're not focusing on the thermistor anymore. We're focusing on the LDR. And I didn't think they'd be particularly good at detecting the light from fires. So maybe, but probably we'd use the thermistor for that one. But for an LDR, so someone's got the idea of street lamps. Great, street lamps. So basically, when it goes dark, it means that the LDR has a change in its resistance again that alerts the circuit, and we might be able to switch on the street lamps. So these are really important components which are useful in everyday life. Okay, so I've got a couple of questions about this circuit then. So if everyone could have a think about, and remember, I just talked you through this, but now I want you to explain it in your own words. So firstly, what will happen to the resistance of the thermostat when it gets hotter? Anyone have any ideas? Okay, so we've got the resistance. Great, so the resistance will decrease. Thinking about our previous graph, the hotter the temperature, the lower the resistance. Excellent. Part two, how will this affect the brightness of the bulb and the reading on the ammeter? So how will that decreased resistance affect the brightness of the bulb and the reading on the ammeter? Firstly, brightness of the bulb. What will happen to the brightness of the bulb? Right, the bulb will be brighter. Excellent. And what will happen to the reading on the ammeter? Great, it will increase. And our final thing is, what then do you think will happen to the reading on the voltmeter? What will happen to the reading on the voltmeter? So the voltage across the thermistor. And again, we've got some answers coming in. Keep it going, guys. Well done. Okay, here we have the voltage decreases, and well done. That's because since the resistance of that of that thermistor has decreased, electrons are losing less energy traveling over that lower resistance thermistor, so it will have decreased. Okay, well done. Good work, everyone, today. So the last thing I wanted to talk about then is the difference between AC and DC. So I've given you a quick snippet. Can anyone tell me what the difference between AC and DC is then? So what is the difference? Can anyone tell me? So DC, yeah, great. So we've got direct current and alternating current. What's the difference then? So that's what their names are. Okay, some good answers here. Okay, so alternating current, as the name might suggest, you're right, changes direction. So it changes direction of the voltage and it changes direction of the current. So one moment the current is going around that way and then it's going around the other way. Change direction all the time, whereas DC direct current doesn't change direction. All right, so Here we have a graph of DC and AC. The top one is DC. We see that the voltage is fixed at one level and it doesn't change from that. Whereas AC, it does, it changes all the time. Where would AC be used, do you think? Where might you find AC in sort of your everyday life? Excellent, mains electricity. Yeah, that's great. So if you plug something into a socket, then what will come out will be AC. Now, most of the time, this is, for example, if you wanted to charge your phone and you plug your phone charger into the socket, most of the time, your phone charger would convert that AC into DC right in the plug. So your phone would only get DC, but nonetheless, out of the socket, it will come out as alternating current. And where would you find direct current? Anyone have any ideas? Where can we get direct current out? Okay, someone said something interesting there, which is motors. Now, motors actually can produce either one. So if you're using you would never really have output out of motors. It would have to be generators, and generators can output either one depending on the structure of generators. So hold that thought. That's for electromagnetism later on. Someone else has put battery. So correct, battery. And I've actually got that on the slide as well. So in a battery, you would find, or in a cell, the ones we've been using all throughout our circuit drawing, you would find direct current. All right, perfect. So that's the end of the content that I wanted to do with you guys today. I've got some questions ready. So just some past paper ones for us to have a look at. But first, does anyone have any questions about anything that we've covered today? And if you don't, just drop a quick no so that I know whether to move on or not. Is there a Kahoot? There is not a Kahoot, unfortunately. I did not prepare a Kahoot for this session, but maybe for next week. So come along, see if I've done one for next week. And no one has any questions? I don't think so. So don't hesitate. If you come up with one while we're doing the questions, feel free to fire it at me. Okay. So first question then. So here's a setup of a circuit. Now it's a little bit unusual because we've got that 12-volt thing. That might be just mains or something, not necessarily a battery, but it's still just a power supply. We've got a variable resistor, which we looked at, and then we also had a heater, which is a component that we haven't really come across, but that's what it looks like, and it's labeled. So firstly, we would have to add a voltmeter to the circuit. And can someone tell me in the chat, I know you can't draw it on, but how would we connect that voltmeter on? You can describe it using technical language or in your own words. Just have a go. Right, so could you please show all the signs? So next lesson, we'll be going through series and parallel circuits. And there I've already prepared all of the signs, all of the circuit symbols, etc., and stuff like that. So join next week and we'll do an in-depth dive for that. But for your simple question there is usually a battery is drawn on like this, right? So that's what we'll be doing next week. So battery looks like this. This is probably a mains output or something. All right, so we've got an answer to the question then. So someone's got, right, so well done. Everyone else, have a go. So we've got answers coming in already. So how would you connect that voltmeter to the circuit? Come on, just have a go. Describe it in words if you don't know the technical term. Any ideas, anyone? Okay, we've got some more answers coming in. Right, well done. So the technical term for this is in parallel, right? You connect voltmeters in parallel, and that just means sort of around on a separate branch. So if I wanted to work out, measure the voltage across the heater, I put my voltmeter here, not on a separate branch. And well done, everyone who got that. Okay, we've got a quick calculation question again. So everyone have a go at part II. So here we're calculating the voltage across the heater. So we're basically predicting what we would see on the voltmeter that we've just connected like that. So once you're ready, just pop your answer in the chat. Now we've got some answers already. Keep them coming, guys. Well done. Okay, perfect. Got quite a few right answers. Everyone, please do have a go and pop it in the chat. If you don't get it, then we'll go through it. Right, I think okay, well done everyone. So everyone who did got 8.4, which is the correct answer. So here, obviously we will be doing V equals IR. So you're doing 15 times 0.56, which is, as you said, 8.4 volts. Well done. Okay, next one. So again, this is a bit of a multiple choice, and then we're seeing what's measured by the meter. So question 4A. So just either put A, B, C, or D in the chat, or the answer that you think. Right, everyone got that really quickly. Remember, it's electrons that are traveling around the circuits. Please don't make the mistake of thinking that they're, the metal ions as well and stuff. It's only the electrons. Okay, and then we've got this circuit just marked on. And I want you to tell me what meter 1 measures and what meter 2 measures. Now just wait for everyone to have a go at this one. Right, perfect. The answer's coming in so far, really good. Everyone have a go, even if you're not sure. Okay, well done. Yes, so meter 1 measures the current and meter 2 measures potential difference. Remember, current, flow of electrons around the circuit, how quickly they're moving. That's the same all around. So we've got to put that right on top of the wire, right? Voltage or potential difference, measuring the difference in energy between these 2 points. So that second one has got to be our voltmeter measuring potential difference or measuring voltage. Right, well done. So we've just got an answer saying meter 1 is resistance. Now, so I hope I've explained why it's current, but that's an interesting question actually. How would we measure resistance? Because we've got this setup, we're not adding or taking anything away. How would we find the resistance of this lamp using this setup? Because I haven't mentioned such a thing as a resistometer. So what would we use? Right, we've got some answers already. Anyone else have ideas? Right, so great. So obviously we already have a voltmeter and an ammeter in this circuit. So it's actually quite simple what we do. What we use is just Ohm's law. We do the voltage that we read off the voltmeter divided by the current that we read off the ammeter. Now, if you really want to be really accurate about this, what you could also do is notice how this has a variable resistor as well. So you could just take one reading and you could say R equals V over I. Or sometimes physicists really like using graphs for these kind of things. So you could also plot a graph of, so specifically V and I here, because this means that you have a graph which basically says V equals IR, where the gradient of this line would be your resistance. But careful about this, because this is only true if you plot the voltage on the y-axis and the current on the x-axis. This is a little bit extra. Know how to calculate it with the equation, but note that there is also the potential of calculating it using a graph. Right, well done, everyone. Okay, so I think last 2 questions for today. Let's have a look at lamp B. So we're using that oh, actually, don't worry about this one. We'll skip over that B question because that's what we'll be doing tomorrow. So what I want you to do instead is skip straight to part C. And someone's in the chat put, or use a multimeter, couldn't use a multimeter. So at GCSE, we typically don't make use of multimeters, and all of the questions are expecting you to be calculating it using the equation. So if you're asked how to do it in a paper, please make sure to give one of the 2 methods we've just talked about. Right, so have a go at question C. So remember, you're going to have to read off the graph for this one. And it's not the gradient method because this is a non-ohmic resistor and you can't use the gradient meter for a non-ohmic resistor. So here we're just using the equation. So can anyone have a go? What would the resistance of this lamp be? And when you've got an answer, just post it in the chat. Okay, we've got some answers coming in. Well done, you guys. So have a go. If you hadn't had a go yet, please do. Right, so the correct answer here, everyone, was 6 ohms. Well done. Sorry, not 6 ohms, 10 ohms. So what we're doing essentially is we're reading off the graph. So we know that the current is 3 amps. So we go along and then we go down and we get a reading of 3 volts. So now all we have to do is use the equation. So we're doing resistance equals voltage divided by current. So we put in our numbers and we get 3 divided by 0.3. So that is an answer of 10 ohms. Well done, everyone. Okay, so that is us finished for today. Thank you. Thank you all for listening. Next week, we will be carrying on with domestic uses, safety, and static electricity. But we've got 4 lectures planned in the series. So next lesson is domestic uses, safety, and static electricity. The lesson after that will be covering series and parallel circuits, going through circuit diagrams and how to draw out different components. And our last lesson will be on, let me just think. It is on electricity and electrical power transfers. So that's stuff like, how do you work out electrical power and what is power in general? So does anyone have any questions for me before I let you all go? Nope. In that case, I will hopefully see you next week at the same time. And thank you all for listening. Bye.